Okay, so today we're going to talk about the exact equations. We talk about the linear equations in 2.3. We got some formulas to solve linear equations. First order linear differential equation that can be solved completely analytically using the integrating factor. Okay, if you remember that. And in 2.2, we discussed separate equations. You can separate variables on the two sides of the equation and they integrate to solve it. So in this section, we're going to talk about another type of differential equation that can be solved completely analytically. And those are called the exact equations. So let's just talk about differential of a function of two variables. Because we know that differential of a function with one variable, f of x is just the derivative of f times dx. So that's f prime dx. In the case where a function z has two variables, x, y. So z is a function of both x and y. Then how do you define differential? So it is defined as dz equals. So dz is again the notation for differential. So that is defined as the partial derivative of the function f or z with respect to x times dx plus the partial derivative of f or z with respect to y times dy. Okay, dx and dy are just the increment or differentials of x and y. So this time you got the partial derivatives. You got two derivatives, and so you will have two terms in the differential. So then the next thing is exact differential. Okay, so what's the mean by exact differential? So a differential expression m, which is a function of x and y times dx plus n, which is also another function of x and y times dy, is an exact differential in the region R of the xy plane if it corresponds to the differential of some function f defined in R. So what it means is you are given an expression, with some functions m and n. They are both functions of x and y. So the expression m dx plus n dy, if it is equal to the differential of a function f. Okay. So then this expression m dx plus n dy is called the exact differential. So basically, this expression can be rewritten as a differential of f. Okay. This looks a little abstract, but as you see some examples later, we're going to show, what it means here. Okay. So then if you have a first order differential equation with the form of m dx plus n dy equal to 0, that is said to be exact equation if the expression on the left-hand side there is the exact differential. Okay, so that means you can rewrite the left-hand side of the equation as df, and the equation then becomes df equal to 0. Okay, then obviously f has to be a constant in that case. All right. If the differential of the function is 0, that means the function itself has to be 0, to be constant, just like a derivative. All right. So then we can solve this differential equation as f of xy equal to c, where c is arbitrary constant. So what it means in this definition, or in this case, is you are given a differential equation in the form of differentials dx and dy. So m dx plus n dy is a differential equation. Okay, it is in the form of differentials instead of derivatives. So how do we solve this differential equation? If you can write down this left-hand side as a full differential, as an exact differential df, okay, then you can solve it easily. And the solution is, f of xy equal to c. So if you look at definition of differential of a function of two variables, dz equals partial f partial x dx plus partial f partial y dy. Because f is a function of xy, when you take the partial derivatives of f with the x or y, then you get another function of x and y for the partial derivative, So, so that makes sense. Okay. But, the question is, we don't know whether m dx plus n dy, the equation itself, is exact differential or not. Whether we can find such f so that, df equals m dx plus n dy. We don't know that. Okay. So the goal is to try to rewrite differential equation as a exact differential on the left-hand side. Okay, so that's the definition and some general discussion of exact differential. All right. Any questions about it? So this is a little abstract, but let's see some examples. Then you know what I mean. Okay. Before we try to solve any problems, let's just start from a theorem. Okay. So how do you know the left-hand side of a differential equation, m dx plus n dy is exact? Okay. How do you know this is an exact differential? Then there is some criterion. So that's what the theorem says. Okay. So let m and n be continuous and have continuous first partial derivative in the rectangular region R defined by x greater than a less than b, y greater than c less than d. So basically m and n are continuous, and the first partial derivatives are continuous. Okay. Then a necessary and a sufficient condition that m dx plus n dy be an exact differential is partial m partial y equals partial n partial x. Okay, so we know m and n are both functions of x and y. So if you take the partial derivative of m with respect to y and take the partial derivative of n with respect to x, and if they are the same, then we know that m dx plus n dy will be a exact differential. Okay. So the key is whether these two partial derivatives are the same. So in that case, we can find this function f so that df equals m dx plus n dy. Of course, because we know m dx plus n dy is an exact differential, so then you can find the function f so that df equals m dx plus n dy. Okay, that's the definition of exact differential. All right. And the solution to the equation, the differential equation of m dx plus and dy equal to 0 is just the f of xy equal to an arbitrary constant c, as we showed on previous page. Okay. So if the differential equation m dx plus and dy equal to 0 can be reading as a exact differential on the left-hand side, df, then the solution to the differential equation will be fxy equal to an arbitrary constant c. Okay. So then that tells us how to determine whether a differential equation is exact or not. Okay. Yeah, you just take a differential of m, partial derivative of m with respect to y, and take the partial derivative of n with respect to x, and see if they are equal or not. All right. And if they are equal, then you can easily solve this differential equation to get a solution f of x equal to c. But this just tells you whether the differential equation is exact or not. It still does not tell you, what this f is. You can find this function f so that df equals m dx plus and dy, but it doesn't tell you how to find f. Okay, so the following procedures are the steps to find this f, or to solve this equation, in details. All right, so we start from the definition of the differential of f. So that's just partial f, partial x, dx plus partial f, partial y, dy. That's the definition of differential of f with two variables, x and y. So if you compare this definition with this condition in the theorem, df equals m dx plus and dy, then obviously m has to be partial f, partial x, and n has to be partial f, partial y. Okay. So then you just integrate, both the equations, then you're going to find the function f. Okay, so m and n are given in the problem. So remember, the differential equation is m dx plus and dy equal to 0. So m and n are the functions given in the problem. And we need to find the f from these two equations, basically. How do you do that? You just integrate one by one. Okay, for example, if you integrate the first equation, partial f with partial x equal to m, you integrate with respect to x. Okay, so then you're going to get a f on the left hand side. Okay, so when you integrate with respect to x, then you treat y as a constant. Remember? So f will be equal to the integral of m with respect to x. Okay, and you treat y as a constant. Plus a constant. Okay, remember that independent of x, because you are integrating with respect to x, then you're going to get a constant independent of x, but that constant could depend on y. So it might be a function of y. It's just independent of x. So we get f equals integral of m dx plus some function g of y. Now we're going to use the second equation, partial f, partial y equal to n. So because f is this integral of m dx plus gy, so if we plug in that f into the second equation here, then you're going to get the partial m, partial y dx. Okay, so just take the partial derivative m with respect to y. Okay, All right. When you take the partial derivative with respect to y, you don't have to worry about the x. Okay. So that becomes the integral of partial m partial y dx. And when you take the derivative of g, you get g prime y. So that's the derivative of g with respect to y. And that has to be equal to n, okay, from the equation itself. So then you can figure out this g from this equation here. So if you move the integral on the left to that right-hand side becomes minus, then you got g prime equals m minus the integral of partial m partial y dx. And then you just integrate the right-hand side, you get the g because you know g of y. And n and the m are given in the problem, remember. So everything is known on the right-hand side. So you just integrate the right-hand side to get g, and then go back to this f equals integral of m dx plus gy. So we found the g, and then you can just integrate m with respect to the x to get f. So that will be solving the differential equation. The solution to the differential equation will be this function f equal to c. So we found this f. The solution to the differential equation is f equal to c. Okay, so that's how you solve this equation. So it's a little complicated, but we're going to see the example. Okay, yes.
X and Y just basically represent 2 points on the graph.
No, x and y are variables. Variables. So we got two functions, m and n. They are both functions of x and y. So m and n both depend on x and y. Okay. So if you take a 2 cal 3, then you know what it means by a function of two variables. Okay. So that's some theories about the exact equations. So let's just try to do some examples and see how we proceed to solve exact equations. So in this example, we want to solve the equation 2xy dx plus x squared minus 1 dy equal to 0. So this is a differential equation in the differential form. If you write the equation in the derivative form, it will be 2xy plus x squared minus 1 times dy over dx. Right? So a differential equation can be written as a differential form or in the form of derivatives. Okay. So and we know dy over dx is y prime. Okay. So let's see whether this equation is exact or not. Okay. First, you have to find out whether the equation is exact or not, then you can proceed. If it is indeed exact, then we can proceed with the steps on the previous page to find the solution. If it is not exact, then you cannot do it in that way. All right. So in this example, m is just the 2xy. Okay, that's the function coefficient for dx, and n is the x squared minus 1. That's the function in front of dy. So how do we know this equation is exact? You just take a partial m, partial y, and partial n, partial x. Okay, so partial m, partial y. So you take a derivative of 2xy with respect to y. So you don't have to worry about the x. So if you take a derivative to y with the respect to y, you get 1. So it's just 1 times 2x. So partial m, partial y is just 2x. And when you take the partial n, partial x, you just take the derivative with respect to x, you get 2x, right? Okay. The derivative 1 is just 0. So you can see they're the same. So partial my partial m partial y equals partial m partial x. So according to the theorem on the previous page, this is a necessary and a sufficient condition to determine the differential equation is exact. So we know this differential equation exact. Then we can proceed to find the solution using the steps on the previous page. And according to the theory, we just discussed the solution to the differential equation is just the f of xy equal to c, where f is the integral of m dx plus gy, where g prime is n minus integral of partial m partial y dx. So these are the formulas we derived from the previous page. Okay, you just use those formulas to find f. All right. So what you do, you're going to find the g first, and then you try to find the f. Okay. So actually, you're going to use this g prime. Okay, to find the g. So g prime equals m minus partial m partial y dx. We know n is x squared minus 1, and partial m partial y is just 2x. So just plug in those, and the integrate 2x with respect to x, you get the x squared. Okay, so everyone knows how to do that. So then you got x squared, negative x squared to cancel. So the answer is -1. So the g is just -1. So if we integrate on both sides, we get the g equals the integral of -1 with the respect to y. So you get the -y. Okay. So we found that gy equals -y. Okay. And we don't have to worry about the arbitrary constant in here. Okay. The arbitrary constant will be at the end of the solution, fx equal to c. So this is just the first step to find g, and then we can use this g to find f. So use the formula for f. So we get f equals the integral of m dx plus g, and m is 2xy, plug in, so integrate 2xy with respect to x. Okay, just be careful about this. You have to specify which variable you are trying to integrate over. All right, you got two variables in the function. Plus gy, okay, we already found gy is just -y. So when you integrate this function with respect to x, you can treat y as a constant that can be taken out from the inside. So you can take out the y from the inside and just integrate the 2x with respect to x. So you get x squared for the integral. So it just becomes y times x squared in the first term, and the gy is -y. So we got this f equals yx squared minus y. So the solution to the differential equation is just fxy equal to c. So we found the f in here, but the solution to the differential equation is f of xy equal to c. Okay, so that's one thing you have to be careful. All right, that's not the solution to the differential equation. That's just the f. Okay, the solution to the differential equation is to the original differential equation is f equal to c. So that's just x squared y minus y equal to c. So usually you put x in front of y. Okay, so then you can actually factor on y on the left hand side of this equation. You get the y times x squared minus 1. Okay, if you do that, and then you divide by x squared minus 1 on both sides, then you get y equal to c over x squared minus 1. So that's explicit solution. All right. So that's the answer for this problem. Any questions about this example? Okay, let's see. Okay, I don't think I want to go on to another example today. Just give you guys a little time to digest this thing. So I'm going to stop the recording and taking some questions.